We're moving on to the next presentation. The next presentation is on the paper Conceptual Modeling of Lifecycle Digital Twin Architecture for Bridges. The author of this paper are Inga Maria Giorgadze, Faridaddin, I cannot pronounce that surname, and Hans Voordijk. I'm sorry, guys.
No, that's good enough. That's good enough.
I'm doing my best. Please, are you ready to go?
Yeah, I am. Thank you very much for the introduction. So hello, everyone. My name is Farid, that guy with that difficult name. I tried to put the shorter version of my name just to make it a little bit easier to pronounce. So I'm an assistant professor from University of Twente in the Netherlands. And I'm going to talk about this very kind of preliminary research that we've done in the domain of developing an ontology for bridge digital twin. Just to give you a little bit of context about how we got to this project and we get inspired actually to do this research. Anyone knows this bridge from the audience? Yeah. So it's a MX3D bridge. And what is unique about this bridge is, well, there are a lot of dimensions of this bridge that is unique in the world. But perhaps what stands out the most is that this is the first fully 3D printed steel bridge in the world that is not only for research purposes, but it's already placed in Amsterdam. So if you ever have chance to go to Amsterdam, go to Red Light District only for the bridge, not for other purposes. It's placed in Red Light District and it's been open a little bit less than a year. So, and that's actually Her Highness, the Queen Maxima, who opened actually the bridge in September. So how we got inspired by for this research, another very unique aspect of this bridge that makes it one of the smartest bridge actually in the world of its kind is that for such a small bridge, we installed about 100 different sensors on that bridge of different types and different kinds. And at our university, of course, this is a very mega project in terms of how it was materialized. There were a lot of parties involved. Autodesk was very actively involved. MX3D was the manufacturer. University of Delft, a couple of universities from UK, and our university's job and contribution to this project was that we actually hosted this project for nearly a year on our campus, and we were responsible for the design and installation of this sensor network. So we put about 100 different sensors on this bridge, so it's really sensor laden, and the data from these sensors are we want to collect all this data and then correlate it with the use and operation data that we collect. The overall idea was actually to put some cameras around the bridge, collect the data of the use of the bridge, and then correlate it with the sensory data. Of course, being in Red Light District, there are a lot of privacy issues. So far, we were not able to put those cameras, but that's overall the idea. And then the ambition was to kind of correlate the life cycle data that we collect with the operation data that is coming from the sensors and try to make sense of how this asset behaved. And of course, Autodesk went the extra mile. They used their Project Dasher platform, which is still in the alpha version, so it's not commercially available, to present a sort of digital twin that represents the state of the bridge based on the sensory data. But then this is only one out of about 1,200 bridges that we have in Amsterdam. So if you really want to have a better understanding about how our assets work, but also at the network level, then the issue of data management becomes quite crucial because although Autodesk was very actively involved, the way that the data is currently managed for this is quite ad hoc. So even in this, what they call digital twin model, this is pure geometry. It doesn't have any semantics. There are other reasons for why they couldn't go for semantic model. I don't know if I have time, but I'll try. So this is a monolithic structure. It's printed as one piece, right? So in conventional bridges, you can actually have naming conventions. You have different parts. You could refer to that. But the first challenge we had with building a kind of semantic model for this is, how do you call different parts of this? There are no different parts. It's printed as one piece. So basically, we could say that there are handrails and the bottom beams, but that's about it, right? So we were discussing that we need to kind of take a more semantic approach towards a model like this, but also taking into account the network level data structure. Then we started looking at the standards data that exist for managing the bridge data. Of course, we have the concept of BRIM. IFC supports part of the bridge data. In the Netherlands, we have also NLSFP, that is a kind of classification, a national classification for assets. There are different object type libraries, OTLs for the bridges. But the main problem that we noticed in all those data structures is that they're mainly designed and structured for the design phase and a little bit support for construction, very little life cycle support in those data structures. So that's the first thing that we noticed. And another thing is that inherently all these models are rather object-oriented. So the data is meaningful as long as you can attribute it to certain objects. But when you look at the life cycle of the entire bridge, then as I showed you, really, specifically in the case of this 3D printed bridge, because it's an uncharted territory, what they want to know is that they didn't have a kind of very homogeneous production manufacturing process. So they want to know how variations in the manufacturing process of different parts affected the performance of the bridge. So you need to be able to also model the processes, the agents, the users of this bridge within that data structure if you want to have a kind of life cycle analysis of the entire bridge and also at the network level. So with that problem at hand, we defined this objective that let's try to develop a conceptual model for the architecture of bridge lifecycle digital twin data that covers some of the requirements of the end users and see how we could actually build up on the model that exists within the BEAM domain to make that models actually digital twin ready. So that's what we call digital twin ready BEAM models. Of course, we wanted to use that bridge case study for this project, but this was not easy because still, I mean, this is kind of very unique bridge. So we took a kind of different approach. We actually, Maria contacted one of the major contractors in the Netherlands, BAM Infra, one of the biggest construction companies in Europe. And then she went on and tried to perform sort of ethnographic research. She was established in that company for about 6 months. And of course, the concept of digital twin being rather new, you don't know exactly what are the expectations and what are the use cases of digital twin. So the first thing that she did, she had a couple of interviews with experts, more in the domain of visions, and tried to figure out what are their expectations, what kind of use cases they could imagine for a bridge, for a digital twin of a bridge. And based on those use cases and requirements, then actually she formulated a sort of information requirement, what sort of information we need in order to support this use cases. And based on that, she looked at the existing data structure. She tried to enhance it, add classes and attributes and relationships that are required to make it more digital twin ready. And then, well, she didn't have much time. It was a master's study, so she did it in the span of 6 months. She did a couple of hypothetical cases studies. We didn't have time to actually implement it. And then also she validated by going back to the same experts, showing them the ontology and getting some feedback from them whether or not this ontology makes sense. So I'm going to go through the rest quite quickly. So, and whatever I'm presenting in terms of the ontology is not the comprehensive picture because simply it doesn't fit in a slide. It's quite a large ontology. So the first thing she did, she looked at the existing ontology. She tried to get actually a kind of comprehensive view of how bridge data is being currently modeled in the industry. And then, as I said, this is again not a comprehensive list. The comprehensive list is much longer. Through discussion with these experts, she came up with all statements that would sort of represent the vision of the company, BAM Infra, in terms of digital twin, and then tried to categorize, actually analyze every one of those vision statements in terms of what are the new links or classes or properties or attributes that need to be added to the existing ontologies or bridge data structures. And based on that, she had this, again, high-level ontological model that would represent, that would provide some sort of support for digital twin-based applications. And the main addition, I would say, is that she tried to also add components for processes, but also agents that are involved in the decision-making process of the bridge. So the case study that she did, well, she had multiple hypothetical case studies based on the use cases that was defined by the experts in the company. But the one that she wanted to actually showcase today for this presentation was how we could update the schedule of the periodic maintenance that would be applied to bridges based on the operation and weather data that you collect over time through sensors. So she actually talked to the experts. She tried to get a complete picture of how this should be done based on the sensory data. And then she added the attributes that are required to a simple BIM model in Revit. And then try to see how she could extract all the data relevant to the weather condition and the use condition, and then correlate it with the bridge condition, the historical data that they had. And of course, she didn't go to the machine learning part, but then this provides the basics for machine learning if you want to be able to predict when the periodic maintenance need to happen. So for that specific case, this is a more comprehensive version of the ontology that she developed. What she did, then she went back and then she tried to identify all the classes that are relevant to this specific case study to showcase that you could extract all the necessary information for this specific use case. And then I guess in her thesis, she had 5 or 6 different use cases. And then for the validation, of course, being an ethnographic research, she went back to the experts, provide them with a questionnaire, ask them a set of questions about the extent to which the ontology is correct, complete, concise, and adaptable or extensible. The main comments that she received in the discussion that she had afterwards was mainly about the adaptability, because they said, well, we have a lot of national standards, but also organizational standards for object types in bridges. And then if this ontology is going to work at the national level, it has to be compatible with that. There are certain compatibility degree, but it's not fully compatible.
Excuse me, we need to start wrapping up because you are over a minute.
I guess it's my last slide or the one before last. So I will be very quick. So the main recommendation, so currently we look at the sensor data from the perspective that each sensor would provide only one or supports only one application, but in future of digital twin, you could potentially have the same sensor, but used for multiple applications. We have single assets that is considered for bridge. Well, in future, you could consider other type of assets and requirements for the element model. You could develop ontologies for the process and agent models. Well, basically she developed part of that, but what she means is mostly to test it for type of applications that relate to processes and agent models. So if I want to wrap up, the main conclusions would be, as far as the competency questions are concerned, the proposed data structure was able to meet the core requirements. It was able to actually deliver all the use cases. The phase validation of the ontology suggests that ontology needs to be a little bit improved to be able to more compatible with the standards, but it's a good starting point. And of course, in future, it needs to be implemented in a more rigorous way and applied in real cases. But of course, we hope that we can use the data from this bridge to test that ontology. Yeah, thank you very much.
So a quick question. We have time. No worries, no worries. We have time for a quick question. Anybody? Well, I'm going to make a quick question to Farid. I absolutely agree that construction, probably the construction stage, execution stage, is one of the most challenging to realize a digital twin. What do you think are the challenges for bridges in the construction stage that represent the hardest, to realize a digital twin?
Well, I can answer. Well, I guess that question could be answered from multiple point of view. But then, as a person who is more interested in simulation of the processes, I guess the most challenging part that I see right now is that you would like to be able to simulate all these processes for more accurate scheduling, and there is no way to develop a structured data that could be used for simulation of processes during the construction. So these simulation models that we develop, it's mostly ad hoc, it's for one specific case. But in future, if we are talking about these modular simulation components that could be used from one project to another or cross projects, then being able to structure those simulation model, construction process simulation models within the concept of digital twin, I guess that's quite challenging.
Yeah, I agree. Thank you very much. Now we